I welcome you all in my YouTube video channel. Today I will deliver lecture on group lecture number 59, in which I will discuss some theorems on automorphism. Now we prove a theorem. Theorem is the set of all automorphisms of a group forms a group under mapping composition. Now we prove this. Let G with binary operation O is a group. Phi be an automorphism. Defined on G if phi is defined on G into G is an isomorphism. Let AG be the collection of all automorphisms defined on group G. Let phi and psi belong to AG. Therefore, phi is defined on G into G and psi is defined on G into G are automorphisms. Implies that phi defined on G into G and psi defined on G into G are isomorphisms. Therefore, composite mappings phi psi G into G and psi phi defined on G into G are isomorphisms. Since domain and codomain of these isomorphisms are same groups, therefore phi psi and psi phi are automorphisms. That is, phi psi belongs to AG and psi phi belongs to AG. Therefore, closure property holds. This is number one. Since composite of mapping fulfill the associative property, therefore composite of isomorphisms fulfill the associative property. This is number 2. Let Ig be a mapping defined on group G into G such that Igx equal to x. Therefore, Ig is identity mapping. We know that the identity mapping Ig is an isomorphism. Since domain and codomain of Ig be same, therefore Ig is an automorphism. Therefore Ig belongs to Ag. This is number 3. Let phi defined on G into G be an automorphism, and let x belongs to G, then phi Ig x equal to phi Igx equal to phi Igx means x, implies that phi Ig equal to phi. This is number 4. Again, Ig phi x equal to Ig phi x, and this is equal to phi x. Since Igx equal to x, therefore Ig phi x equal to phi x, implies that Ig phi equal to phi. This is number 5. From 4 and 5 we get phi Ig equal to Ig phi equal to phi. Therefore Ig be the identity element of Ag. This is number 6. Now let phi defined on a group G into G is an automorphism. Therefore phi belongs to Ag. This is number 7. Implies that phi defined on G to G is an isomorphism. Implies that phi inverse G to G is an isomorphism. implies that phi inverse, here domain and codomain be same and it is an isomorphism, therefore phi inverse G to G is an automorphism, implies that phi inverse equal to phi inverse phi equal to identity automorphism. Therefore, phi inverse belongs to AG and phi inverse is the inverse of phi. This is number 8. Therefore, from 1 to 6 and 8, we get that AG fulfills the closure property, associative property, existence of identity element and existence of inverse. Therefore, AG is a group under mapping composition. Now we prove the next theorem. Let G be a group and mapping alpha defined on G into G is defined by alpha A equal to A inverse. A belongs to G. Then alpha is an automorphism if and only if G is abelian. Now we prove this. Given that G is a group and alpha is a mapping defined on G into G such that alpha A equal to A inverse. A belongs to G. Let this is number 1. Now let A B belong to G implies that alpha A equal to A inverse and alpha B equal to B inverse. Let this is number 2. Now let alpha A equal to alpha B implies that A inverse alpha A equal to A inverse equal to B inverse. Taking inverse in both sides, A inverse whole inverse equal to B inverse whole inverse implies that A equal to B. This is number 3. Therefore, alpha is 1-1 mapping. This is number 4. That here this is group G and also this is group G and alpha B a mapping image of A is A inverse. Let B belongs to G. G is a group. Implies that B inverse belongs to G. This is the group G and this is also group G. We may write here B inverse. Now, alpha B inverse equal to B inverse whole inverse implies that alpha B inverse equal to B inverse whole inverse means B. Therefore, for any B belongs to G codomain, there exists B inverse belongs to G. This is domain such that alpha B inverse equal to B. Therefore, alpha is onto mapping. This is number 5. From 4 and 5, we get alpha G to G is 1 1 onto mapping, implies that alpha defined on G into G is bijective. This is number 6. Now, let AB belong to G group, implies that A operation B belongs to G. Closure property. And A inverse B inverse belong to G since G contains inverse. G is a group, so for each element in G there exists an inverse. Let G is abelian. Now, alpha A operation B equal to A operation B whole inverse. This equal to B inverse operation A inverse. This equal to A inverse operation B inverse. Since G is abelian, means commutative property hold in G, and A inverse equal to alpha A operation B inverse equal to alpha B. Let this is number 7. Therefore, from 7 we get alpha is homomorphism. This is number 8. From 6 and 8 we get, in 6 alpha is a bijective mapping, and in 8 alpha is homomorphism. Therefore, alpha defined on G into G is an isomorphism. Here domain and codomain be same. Therefore, alpha is an automorphism. Conversely, let G be a group and alpha defined on G into G is an automorphism such that alpha A equal to A inverse. A belongs to G. We have to show that G is abelian. Let A B belong to group G implies that A operation B belongs to group G. Now, alpha A operation B equal to alpha A operation alpha B, since alpha is homomorphism. As alpha is an automorphism, means alpha is an isomorphism, and if alpha is an isomorphism, then alpha is bijective and alpha is homomorphism. So here we have taken the property alpha is homomorphism. Implies that here alpha A equal to A inverse, means A operation B inverse, alpha A operation B means, and alpha A equal to A inverse operation alpha B means B inverse. Taking inverse in both sides, we get A operation B inverse whole inverse equal to A inverse operation B inverse whole inverse. This is equal to A operation B inverse whole inverse means A operation B, and this means B inverse whole inverse operation A inverse whole inverse, implies that A operation B equal to, this is B inverse whole inverse means B operation A. Therefore, commutative law holds in G. Hence, G is an abelian group. Proved. Now we prove the next theorem. Let G be a group, G is capital G, be a group, and small g belongs to capital G. Then mapping I small g defined on G capital G into G defined by I small g x equal to G x G inverse. X belongs to G is an automorphism of G. Now we prove this. Given that this capital G be a group and small g belongs to capital G group, the mapping IG defined on group G into G such that IGX equal to GX G inverse X belongs to group G. We have to show that IG is an automorphism of group G. Firstly, to show IG is 1 1. Let AB belong to group G, then IGA equal to GA G inverse, IGB equal to GB G inverse. This is number 1. Let IGA equal to IGB implies that GA G inverse equal to GB G inverse. Using cancellation law, A equal to B. Using cancellation law, therefore IG is 1 1 mapping. This is number 2. This is G, group G. This is also group G. This is IG mapping. Let B belongs to group G codomain. This is domain and this is codomain. Now, to show IG is onto, let B belongs to G codomain. Here B belongs to G codomain. Since G inverse B G belongs to G, group G. Since G is an element of group G, therefore G inverse is an element of group G. And by closure property, G inverse BG belongs to group G. Now, IG G inverse BG equal to G inverse BG and here G inverse. This is equal to G inverse B and G inverse. This is identity element of group G. B. This is also identity element of group G. This is equal to P. Therefore, for any B belongs to group G codomain, there exists G inverse BG belongs to G domain such that IG G inverse BG equal to B. Therefore, Ig is onto. This is number 3. From 2 and 3, we get Ig is 1 1 onto mapping. That is, Ig defined on G into G is bijective. This is number 4. Now to show Ig is homomorphism. Let X, Y belong to group G, implies that X, Y belongs to group G, X operation Y. Now, Ig X, Y equal to G X, Y, G inverse equal to G X, G inverse G means identity element, and this Y G inverse, since G inverse G is identity element of group G, equal to G X G inverse and G Y G inverse. This is IGX and this is IGY. This is number 5. Therefore, from 5 we get Ig defined on G into G is homomorphism. This is number 6. From 4 and 6 we get Ig defined on G into G is an isomorphism, because from 4 Ig is bijective and from 6 Ig is homomorphism. Therefore, Ig is an isomorphism. Since domain and codomain of Ig are same, therefore Ig is an automorphism. Proved. Here we have a note. If small g belongs to ZG, means center of group, then Ig reduces to identity automorphism. Here given that small g belongs to ZG, this is center of group. Therefore, Gx equal to Xg for all x belongs to group G. That this is number 1. Since Ig x equal to Gx G inverse, since Gx equal to Xg, G inverse using 1, this is equal to X identity element of group G equal to X. Therefore, IGX equal to X. This is equal to identity automorphism of group G. IG be the identity automorphism of group G, implies that this Ig small g equal to I capital G. Therefore, Ig reduces to identity automorphism of group G. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.